Okay, design and safety factors. Why do we use safety factors? They basically lead to us having to over-design. Many of them are specified by law, by statute and code. They're very important. The reason we have safety factors is we can calculate loads, we can calculate stresses and strains, but there are many, many things about designs and materials that we just can't ever know. Starting from the bottom, micro cracks and voids. Materials aren't perfect. We talked about dislocations and grain boundaries, which aren't necessarily deleterious, bad defects, but they control material properties. We can get real defects, processing flaws, things that will definitely compromise the strength of a material that you don't know is there. The whole field of non-destructive evaluation and testing is intended to show those up, but no inspection method is perfect. The other thing that's not shown on this slide is how your customer might use your material. Just because somebody says they're going to take it to a certain temperature doesn't mean they won't inadvertently overcook it. Maybe people don't know exactly what their loading is. Maybe there'll be a loading factor that no one had counted on. Sometimes even a big safety factor won't account for that, but it at least accounts for a certain amount of human uncertainty in a design. For your supply chain folks or business people buying materials, probably one of the biggest things you need to understand is that published properties usually correspond to the statistical mean of what the vendor tested. So now you got two factors of uncertainty. What did they actually test? How long have they been producing this material? How big is their statistical sample? How big is their N? And then what they publish is usually the mean. How broad was that distribution? Because guess what? You better be designing to the minimum. What's their 3 sigma? Could be a lot lower. So using a safety factor just accounts for all of this stuff that, while it may be possible to find out, it's not always practical to find, and in some cases, might not even be possible. And so a balanced approach to design and safety factors is not to assign so high of a safety factor that your design is impractical, it's too heavy, that can have energy consumption consequences today as well as cost, but certainly isn't unaffordable. But you also don't want to under-design to the point where one of these unknowns can rear its head and cause an in-service failure. Okay, so all that. What is a safety factor? It is literally the ratio of the calculated stress, what you think you need, and what the design stress is. And it's always a number larger than 1. So if you calculate that you need 100 psi for a given material and you want to assign a safety factor of 2, you would not allow a design stress more than 200 psi. So it's what you calculated that you needed and then what you allow. So in that case, you would not select a material that gave you less than 200 psi for whatever stress that was, which in this case would probably be yield. So working stress just simply goes the other way, but it's approaching it from the standpoint of something that you really want to avoid, a critical stress. So say you knew that you had a yield stress or a fracture onset type of stress of 1,000 psi. You would not allow a working stress that was more than that 1,000 psi divided by your safety factor. So in this case, the working stress would be a smaller number. So in this case, the design stress on the top is what you're designing the material to meet the calculated need. So a higher safety factor means you get a stronger material, and working stress means you're going from the basis of a material can take no more than a certain amount. You're dividing by a higher safety factor, which means the applied working load drops. And that's something that you can work out with some exercises. And that concludes our lectures on mechanical properties. This is the last of 3. We will move into strengthening mechanisms with the next lecture. And as a warning, since these were fairly calculation and application heavy concepts, please be prepared to review the book and work any kind of graded exercises that you might have received, because that's how you'll really lock these concepts in and make them real. It's like a bit more like a math class for this chapter. You'll have to do the problems to really get it. But it will be worth it as we dive into future chapters, because you'll be able to use these concepts to truly fabricate and design real materials and then work to keep them from failing in service, which we will hit next time. Thanks.